In today's video, we're going to talk about acids, and we're going to go over the reactions of acids, the definitions of acids, and talk about strong and weak acids. And first of all, acids, we've done this diagram here. You can see red and yellow. That's because when you put them in universal indicator, they'll give you a red, orange, and a kind of yellow colour. Just remind you about GCSE. And remember, hopefully from GCSE, that they're corrosive and you have to wash them off if you get them on your skin. And the definition, again from GCSE, this is the Arrhenius definition, which is they dissolve in water to produce H+. Now, another definition you're going to come across is called Bronsted-Lowry, which says they are proton donors. You may have heard that before, but you won't really have to use that in the first year of A-levels. You will definitely have to use it in the second year. So I'm going to talk about it here now, but I won't use it as much as I use dissolving water to produce H+ ions. Now, types of acids that you're going to come across. So you're going to come across hydrochloric acid in terms of stomach acid, battery acid, sulfuric acid, nitric acid used to make fertilizers, and you're going to come across ethanoic acid to make esters and vinegars. Okay. Now they're there to highlight the fact that you come across them all the time. So you're expected to know all of these formulas, and you expect to use them in balanced chemical equations. Let's talk about alkali. Again, reminder of the colours, blue through to purple. Okay, that's what the colours you get when you add universal indicator to an alkali. Still corrosive, still not very good for you. You've got to wash it off if you get it on your skin. And this time it dissolves in water to produce OH- ions, so aqueous OH- ions. Again, that's the Arrhenius definition. And then we've got the Bronsted-Lowry definition of a proton acceptor. Now, if we carry on from this point, what type of alkalis are you going to come across? The type of alkalis you're going to come across are magnesium hydroxide, which is used as an antacid, okay, and ammonia, which is used to make fertilizers with HNO3, and KOH. Okay, because if you add it to HNO3, you can make nitrates, which are used as preservatives. But the three main ones we'll talk about are KOH, NH3, and MgOH2. Now, Arrhenius and Bronsted-Lowry theory. Okay, now the Arrhenius, as I said, was dissolving in water to produce H+ ions. But I will mention proton donors. I just want to get you used to using the word proton. Now, you think of a proton as a proton is in the nucleus and it's positive. So I've drawn one proton here as a positive charge. This is hydrogen, so it's got one electron going around the outside. Now, H+ ions. So we've got H+ ions here that we're talking about. When we make H+ ions, that electron will be lost. Okay, so as you can see there, it's lost. That means a H+ ion is essentially a proton. So therefore, that's why you'll hear people say it's lost a proton, gained a proton. What they mean is it's lost a H+, it's gained a H+. So proton donor just means I'm donating H+. Okay, proton acceptor means I'm accepting H+. But that's why we call it a proton. Now, an example of this in terms of an acid and dissociation, we know when it dissolves in water, it produces H+. So here's your hydrochloric acid. It's dissolved in the water. As it dissolves in the water, it makes H+ and Cl-. Okay, and that's our proton. Now, I'm going to draw that in a little bit more detail in a minute. But your diagram here, your definition here for a base is going to be neutralising an acid. So very simple, neutralising acid. In AS, it's neutralising an acid. In A2, or second year of A-levels, it will be proton acceptor, like we've said. Now, an alkali is a special type of soluble base, so it dissolves, and that's why it produces the OH- aqueous. And as I said, bases are proton acceptors. And one of the most common examples of an alkali is going to be NH3. Now, you wouldn't think that NH3 would immediately be an alkali because you think, well, where's the OH-? But the OH- comes from the fact that NH3 reacts with the water. The water acts like an acid because it's got a H, which it donates, so a proton donor. Or you can think of where it produces H+ when dissolved, well, itself essentially. Okay, so this H goes on to the NH3 and you get NH4. So it's donated the proton and the NH3 has accepted it. But at the same time, that satisfies proton acceptor, proton donor definition because the NH3 has accepted a proton. But it's produced an OH minus at the same time, because when you take away H plus from H2O, you leave OH minus. So it satisfies the criteria for producing OH minus ions. So when dissolved in water, produces those OH minus ions. Now, we're going to talk about strong and weak acids. Now, you notice in the last page I just drew examples of these equations. But actually what happens is that you get a reversible reaction. So a strong acid is described as fully dissociated. An example is HCl, H2SO4, or HNO3. So we've already seen HCl, so let's go for HNO3. So if I have HNO3, okay, that's aqueous, because all these, it's not an acid unless it's dissolved in water. Okay, but this time I'm going to draw a reversible arrow. Now that reversible arrow says that there's a reaction going that way and there's a reaction going this way. All right, now, so there's your reversible arrow. Now that produces the H plus, the proton, okay, and then it produces the negative ion. Okay, so we've got the cation, which is the H plus. We've got the anion, which is the NO3 minus. And we've got reversible reactions. What actually happens in acids is there is a reversible reaction all the way through, and so it's always reacting that way and then reacting that way, and constantly in a cycle. And you'll talk about it later in terms of equilibrium. Now what happens is, when I say fully dissociate, I'm saying that the actual rate of reaction of the top reaction is way over this way. So it is going so far that way that really you only get these two products. You don't have any HNO3. It's all the way over to the right. So we've just got loads and loads and loads. And that's what I mean when I say fully dissociated. So when I say fully dissociated, that's what I mean, okay? So it's all the way over to the right. Now, weak acid is partially dissociated. So it's partially dissociated. And the weak acid we mentioned at the start was ethanoic acid. So ethanoic acid is very similar in terms of you will have CH3COOH, and again, it has to be aqueous. It is an acid. Definition of an acid involves it being aqueous. I'm going to draw the arrows in a bit of a funny way. You don't have to draw it in the way I'm going to do here. I just want to show that which direction the rate is going as, in which is the highest rate. So I'm going to draw a tiny little arrow going that way, and I'm going to draw a big arrow going that way. And all that's saying is, look, I'm going that way more than I'm going that way. That means it's partially dissociating. What I do is I lose this hydrogen off the end, and when I lose the hydrogen off the end, I have plus H plus okay, and I have my H plus AQ right there. So we have got an equilibrium going where it's to the left, and it's to the left, so mainly this, not very dissociated very much, that's why I've drawn that big arrow there. There's a little bit of this, but not much, mostly this side, and then we've got fully dissociated on this side, so it's all the way over to the right-hand side. Okay, and that's the difference between fully dissociated and partially dissociated. Now, what's really important as well is that you recognise that these acids, which you'll see a lot, these are carboxylic acids, tend to all be weak acids. So if you come across them, you'll know that that's a weak acid before the question perhaps tells you. And their pHs are between 4 to 6-ish, okay, and then the stronger acids are 1, 2-ish, okay, and there's a bit of overlap there in the 3 bracket. And you can see that when you put them into universal indicator, this will be red, okay, and this will be yellowy orange. Okay, so that's the difference between the two. But in terms of exams, the most important thing is that you can describe what a strong acid is. It's fully dissociated. A weak acid is partially dissociated. When it comes to bases and alkalis, you can talk about them in exactly the same way as you can talk about acids. So a strong base is described as fully dissociated. That means if it's an alkali, this means that the OH minus has become fully ionized. Okay. Now, we won't go into too much detail about bases and bases as separate to alkalis. So let's just think about alkalis for now. Which means the OH minus has become fully ionized. So the examples I want you to think about: magnesium hydroxide that we said at the start, and KOH and NaOH. Now, NaOH, basically, if we put it into an equation, we can say, right, it's aqueous, it's fully dissociated, it's created the Na plus, the OH minus. So it fulfills the criteria for an alkali because it has OH minus, aqueous OH minus. Okay, and it's strong because it's fully dissociated. So the equilibrium is all the way to the right. You only get this, you only get these two. Okay, weak base is partially dissociated. And all we need to know about that is, one, it's partially dissociated, but two, what are the common examples? Common examples are carbonates like sodium carbonate. Now, we're going to talk now about a salt so that we can actually start doing reactions of acids with different compounds. So a salt is a chemical formed from when the H plus has been replaced by something else. So in H2SO4, you would take the H plus off and put a metal like NH4 there, or HCl, you take the H off and put a metal like NH4 there, for example. As well as that, you need to remind yourself from GCSE that hydrochloric acid makes chlorides, sulfuric acid makes sulfates, and nitric acid makes nitrates, because we're going to use all of those examples in the next few slides. So common reactions of acids are the fact that they react acid and alkali, which is probably the one everyone is familiar with, makes metal hydroxide plus water. Now, if you look here, let's talk about the salt. Originally, you've got sulfate and the hydrogen. This is your H+. The H+ has been replaced. You can see the sodium is in the place of the H+. That means that's a salt. The H+ has been replaced by a positive ion such as sodium, and therefore that's a salt. Also, you're producing water. That's a really important thing. If it's neutralisation, you will produce water. Okay, so it's a good sign of neutralisation. Now, the hard thing is that neutralisation doesn't always involve production of water, but in most cases it does. Now, we've said here, look, the H+ is in red because that's the colour of it in pH, colour of H+ in universal indicator due to its pH, and the OH- is purple due to its pH in universal indicator. Okay, so look for that water for a neutralisation reaction. Now, acids also react with ammonia to form ammonium salts. So here we have our ammonia. It's reacting with our acid, this time a nitrate. Okay, the H+ has been replaced again. Okay, but it's been replaced by an NH4 this time. So we've got NH4 replacing it this time, ammonium nitrate. And you can do that with like ammonium sulfate, ammonium chloride. Next one is reactions of acid with carbonates. Remember, the carbonates are weak bases, and it's an acid plus metal carbonate goes to a salt plus carbon dioxide plus water. Now, if we look here, we can see that hydrochloric acid this time, H has been replaced by a sodium again. So the sodium has replaced it, therefore that's a salt. We can also see that water is produced. Okay, because water is produced, highly likely this is a neutralisation reaction, and also at the same time, hydrochloric acid is a base, sodium carbonate is a base. Now, all the three reactions we've done so far are all neutralisation. That's because you've had an acid and a base added together. They haven't all produced water, but they've all had an acid and base. Last one is reaction of acid with a base, like a metal oxide. Now that produces a salt plus water, and this time we've got a nitric acid, which produces a nitrate, and this is a copper nitrate right here. The H has been replaced by a copper, okay, and it's produced water, so definitely neutralisation reaction. Now, I've shown you this question because this is very common in exams. So, which equation does not represent a neutralisation reaction? So I've talked in the last couple of slides about we need to produce water, but I also said at some point that it's not always water, it's mostly water. So if we want to do a quick look at this, we can look at B and we can see, oh look, there's water, so this is going to be neutralisation. Oh look, there's water, it's going to be neutralisation. Okay, so B and D are probably, we need to do another check, probably neutralisation. So they are not going to be the answer to the question because we want to know which one doesn't. Okay, now the second check is look for an acid and a base. So if we go from the top here, top says zinc. Is that an acid or a base? No, it's not. It's just a metal. So that's a metal plus an acid. Well, that looks like it's not neutralisation because it's not an acid plus a base. It doesn't produce water either, okay, but it's not an acid plus a base. But let's check by going through the other few. So we've got weak base, carbonate, plus an acid. Well, and it produces water, definitely neutralisation. And then we've got a base plus an acid. There's no water, but it is still a base plus an acid, so therefore that's neutralisation. And then we've got a base again plus an acid, and we produce water, so definitely neutralisation. So the answer is most definitely A. Now the reason is because we looked at our definition of neutralisation, and we looked to say it's a chemical reaction in which an acid reacts with a base, and that's what we checked, to form a salt. And I put in brackets and water. It's not necessarily always water, so don't get caught out because you think it always has to produce water. It doesn't. It's just the acid plus a base.